Okay, so my recording, yes. So hello everyone. Going to start a minute early. So welcome back to your Comp 335 tutorial. So in this tutorial, we're going to first be discussing DFAs. So we're going to look at the DFAs that you saw last week, and then have a discussion about regular languages. And so these two NFAs and NFA to DFA, I already have some pre-recorded material that I think, because I'm not going to have time to cover it in the tutorial, so I'm going to post it when I post the tutorial recording, and you can have a look. Maybe it'll probably be helpful for your assignment and quizzes. If there are any doubts about this, then we'll talk a bit more about NFAs and NFA to DFAs on tutorial 3. But I do think the recordings are pretty, I think, and they cover everything in these slides. So I think they should be enough. But if they're not, just shoot us an email and we can talk about them or discuss them in the next tutorial. Okay, so enough said. Let's talk about DFAs. So the first two slides of this set aren't in the ones that you have because they're just theory. So I'm just going to quickly refresh your memory about what a DFA is, and then get to solving some exercises. So just a reminder, what is a DFA? A DFA, or a deterministic finite automaton, is a 5-element tuple M, where you have a set of states, an alphabet, a transition function, an initial state, and a final state. And so you can think of your DFA as is just this black box where you start in Q0. So you start in Q0, and starting at Q0, you have an input string, and you're going to follow that input string throughout your machine, and you're either going to end up in a final state, which at that point means that your machine is going to accept the input string, or you're going to do a computation and you're going to end up in a non-final state, which means that your machine is going to reject. Okay, so a very important concept is that a DFA either accepts or rejects. It does not create or generate strings. It only accepts or rejects them. So it's only kind of binary return. It's either a yes or a no. Okay, and another important concept to know about DFAs is the transition function delta. Delta is essentially what allows you to go from one state to another. So if you're in, let's say, Q1, and you read an A and you go to Q2, well, this can be written with the delta transition function as delta if you're in Q1 and you read an A, then you go to Q2. Okay, so that's how you would read the transition function. Okay, so now that we have that kind of global idea of DFAs in our head, let's just talk a little bit about what it actually does with respect to languages. So when we have a machine DFA M, and we consider all of the strings that are accepted, by M, then this set of strings, this language denoted L of M, is known as the language accepted by the DFA M. Okay, so remember, as I just said before, a DFA accepts or a DFA accepts a language. It does not produce a language. Okay, so that's very important to make to distinguish between those two concepts. And if you want just a bit more formally, L of M is the set of all strings over sigma, where once you start at that input, and once you start at the input at the initial state Q0, and you read that string W, in 0 or more steps, you're going to end up in your final state. Okay, so this is just a fancy way of saying that you start at Q0, and if you start at Q0 and you can sort of generate a path to go to a final state QF, then this string W is going to be in L of M. Okay, so that's enough about theory. Now let's actually look at some examples. Okay, so I have the following DFA here, where let me just point out a few aspects. This is the initial state. These are the transitions. These are a few of the transitions, which are just outgoing edges from Q0. This is a final state, and this is a non-final state. And in fact, because it's a non-final state and there's a loop, there's a self loop on it, it's also referred to as a trap state. Okay, it's a trap state because once you enter Q1, if you read anything else, once you're in Q1, then you're going to stay trapped in Q1. Okay, so for instance, just to remind you with the delta, if you're in Q0 and you read a 1, so that corresponds to this transition here. So if you're in Q0 and you read 1, you're going to go to Q2. So delta Q0, 1 would be Q2. Okay, so fairly straightforward notation. So now let's look at let's trace some inputs and outputs. Bryden, oh, hi Bryden. That's a good question. No, it's not a trap state because we solely refer to a trap state as a state where you're always going to reject. Okay, so Q2 is not a trap state because if you end up in Q2 and you read any number of strings, you're going to stay in Q2 and accept. Okay. Yes, trap state is a state from, yes. Yes, I am. The tutorial is recorded and I'm going to post it and an extra kind of recording for NFAs and NFA to DFAs. No problem. So what was I saying? Yes, okay. So now we want to trace some input and output. Essentially, given this input string, I want to see whether the DFA M is going to accept it or reject it. So I start my tape or my cursor always starts at the leftmost symbol, and even before that, even before I start at 1, I'm actually going to start right before it, and that corresponds to starting in Q0. So you start in Q0, meaning you haven't read anything yet, and now you start to read. So now you start to read symbols. So the first symbol you read is going to be a 1. So from that 1, now that you're in Q0, you're going to read a 1, and you're going to go to Q2. Okay, so now you're in Q2. And now that you're in Q2, you're going to read, so you're going to move your cursor here. You move your cursor, and you read a 0 from Q2. So with this transition, this tells you to go back to Q2. And in fact, you can see that no matter what you read here, you're going to stay in Q2. And because Q2 is a final state, so there's a double circle, meaning that it's a final state, your input 101 is going to end in Q2 in a final state, so it's going to be accepted. Okay, because you end up in a final state, you accept your input string. All right. Now let's look at a case where you get a reject. So a very similar example, except that now you start. So you start your cursor right before, and that corresponds to starting at Q0. Okay, and now instead of reading a 1, when you move your cursor, you're going to read a 0, and that's going to bring you to Q1. And then now that you're in Q1, you're going to move your cursor again, go to 1. So you're reading a 1, and you're in Q1. So you're going to loop back to Q1. So then you move your cursor again, you're in, now you're reading a 0, and you're still in Q1, and you read another 0. You read that 0, and you're back in Q1. Okay, so that's a lot of words just to say that once you're in Q1, you just can't get out. It's like a black hole, essentially. You just can't get out of it, okay? And because your input ends, so your input is done, right? You finish reading your input, and you're in a non-final state. Because of that, you say that M is going to reject your input string W010. Okay, so that's the tracing the input, and clearly we can see that if you want to generalize which inputs are accepted and which are not, you can see that if you're in Q0 and you read a 1, so in other words, if your first symbol is a 1, then you're going to end up in Q2, and then after, once you're in Q2, you're going to, yes, very good. You're going to, I mean, it's right, yeah. Anyways, you're going to accept any other string that comes after. So you're going to accept any string that looks like 1W, where W is in 0, 1 star, and you're going to reject any string that starts with a 0. So meaning that the language accepted by M, or L of M, is the set of strings over 0, 1, where W starts with a 1. Right, so a fairly straightforward conclusion. Okay, so now that we've seen an example on tracing, let's do an example on constructing a DFA. So what is this? This is just telling you that basically there are different types of languages that can be accepted by DFAs, and depending on that type of language, depending on the kind of construction or kind of property, you're going to need a different technique or a different trick to make a DFA to accept it. And essentially, we're just going to cover a few tricks. There are a lot, but we're going to, these examples try their best to look at a few of them, okay? So then this just gives you a more a theoretical way of solving it. I think the best way is actually to just go straight to the example and take it from there. So here my language L, which I want to accept, is the language of strings over the alphabet 0, 1, where the string W contains 0, 0 as a substring. Okay, so what does this mean? Well, I definitely accept 0, 0 because 0, 0 is a substring of 0, 0, clearly. What else do I accept? Well, I can accept something like 1, 1, 0, 0, 1, or something like 0, 1, 0, 0. But I can't, so these would all be accepts, but I can't accept, I will reject something that looks like 1, 0, 1, 0, right? This is going to be a reject, okay? So how am I going to essentially build a DFA that looks like this? Well, for substrings, for substring constructions, one good trick that I find is you first start, you essentially create your structure for accepting a substring, okay? So you know that to accept a substring 0, 0, you need to start at Q0 and you need to read a 0 and then read another 0. So once you've read 2 consecutive zeros, once you've gone through this transition and then this transition, you know that whatever else happens, so whatever else comes after the 0, 0, you're going to accept that, okay? So that means that once you're in this guy where you know that you read 2 zeros, you're going to accept anything else. So that's why there's, once you're in Q2, you're going to have transitions 0, 1 back to Q2. So this is going to be a final state. And essentially anything after, this is just saying that anything after 0, 0 is going to be accepted. Okay? So now that I have the basic structure, I have my 3 states here. All I need to do is fill in the transitions, okay? Because I know in a DFA, every state has to have exactly 2 transitions. So here I have 2 transitions. Here's the 0 and the 1. For Q0, I have the transition for 0, but not the transition for a 1. Okay, so what happens when I'm in Q0 and I see a 1? Well, basically what's going on is I'm reading my input. I'm reading my input and I have a 1 and maybe I have a bunch of 1s, okay? All these 1s are not contributing to finding 0, 0, right? Because As long as I'm seeing a bunch of ones, that doesn't bring me closer to the goal of seeing 0, 0 as a substring. So that means that if I'm in Q0 and I keep seeing ones, I can just stay at Q0. And it's basically, I'm just waiting. I'm waiting for a 0, 0. And if it doesn't come, if essentially my string is just a bunch of ones, then I'm just going to stay in Q0, and that's going to be a reject, right? Because it's not a final state, so it's going to reject if I end there, okay? So now I know that Q0 has two transitions. So this guy is good, I have two transitions. This guy is good, I have two transitions. The only thing left is this guy. How do I fill the gap for kind of the extra transition when I'm in Q1 and I see a 1? Well, when you're in Q1, what has actually happened? So what has happened is if you're in Q1, you saw maybe a bunch of ones, and now you've just seen a 0, right? You've just seen a 0. And now what's going on is you're going to see, so you're in Q1, you're going to see another 1. Actually, what happens now that you've seen that 1 is you need to reset your search for the substring 0, 0. Because the fact that now you have a 1 means that all of your searching here was basically useless. This 0 wasn't the first 0 in 0, 0. So you need to reset your search. And that's why once you're in Q1, you reset your search all the way back to Q0. And then it's essentially like you're starting the search again from Q0. Okay, and now you can see that I have two transitions for each state. So clearly this is a valid a DFA, it's a valid transition function, transition diagram, sorry. And so I can see that this is a DFA M such that L of M is equal to L. And I know this just by exhausting all the kind of scenarios that can occur. Okay, so I hope that's clear. Of course, let me know if it's not. But if it is, then that was the first example of constructing a DFA. What time is it? Okay. So now another type of language for which you'd want to construct a DFA is one where you essentially have you're looking for a specific number or a particular even or oddness of the number of zeros, the number of ones, or of your length. Okay, so for instance, here I have the language L1 over the strings, over the symbols 0, 1, where W should contain an odd number of zeros. Okay, so for instance, 0 would be accepted, 0, 0, 0 would be accepted or would belong to L1. Then if I have a bunch of ones after that, it doesn't matter, right? I would still have an an odd number of zeros. But something like 0 and then a bunch of ones and then 0 would be rejected because it has two zeros, which is even. Okay. So the way to do it for this type of example is you essentially make cases. So Q0 is going to be the case for even number of zeros, and Q1 is going to be the case for odd number of zeros. Okay, and the reason why Q0 is the case for even number of zeros because when you're in Q0, so imagine this is your input string. When you're in Q0, your cursor starts before, right? Because you could technically accept the empty string. Okay, so at this point, at this moment, when you're in Q0, you essentially have no symbols, right? So your length is 0. So now it's going to be a bit confusing, but try to follow me. You have no zeros, right? So 0 is an even number, right? So that would mean that Q0 is the case for even number of zeros. It was a mistake of choosing 0, 1 and even number, but anyways, hopefully that's clear. So that's why Q0 is the case for even number of zeros. And then once you're in Q0, right? So you have an even number of zeros and you read a 0, then you swap the parity. You swap the parity from even to odd. So now that you're in Q1, you have an odd number of zeros. So imagine you just saw a 0, right? So you didn't see anything, now you saw a 0, so you go from having an even number of zeros to an odd number of zeros. And then if you're in Q1, so suppose you're in Q1, you read an odd number of zeros, so you have 3 zeros, and now you read another one. So now you have an even number of zeros, so you go back to Q0. Okay, so that's the essential, that's the kind of most important mechanism for this DFA. And then the extra ones here to make the DFA valid, well, what you need to essentially think about is no matter if you have, let's say, 6 zeros, suppose you have 6 zeros, it doesn't matter how many ones come after that. That's not going to change the fact that you have an even number of zeros. So that's why the ones here stay in the same place, because they don't change the parity of the number of zeros. Okay, and because I'm looking for odd number of zeros, I would make Q1 the final state. Okay, and so this would be what would this be? This would be the DFA that accepts the language L1. Okay, so there was a question for this question. Can we draw it another? It's possible, yes, to draw it another way, like having 2 final states instead of 1. Continue after Q1, okay, with 2 more states, which goes straight with 0. Okay, it's very difficult to answer a question like that because you can't really draw it for me, but I'm trying to picture. So this is definitely the simplest DFA, but there's actually an infinite number of DFAs that can be created to accept this language because it's an infinite language and it's regular. I'm just trying to continue after Q1 with 2 more states, which goes straight with 0. So I'm having a lot of trouble kind of picturing how the 2 states would work. But I mean, I certainly think it's possible if you draw it correctly, and if you can exhaust all the cases and it seems like it's working, it's probably definitely valid. It's just, this is kind of like the minimal DFA. It's the DFA that uses the least amount of states and also least amount of drawing and ink. But yeah, I'm sorry, I can't answer that question better because I can't, yeah, sorry. Okay. So that was for this example. Then we have a very similar example here, where you want, now you want to accept strings over 0, 1, which have an even number of ones. So I'm not really going to go through the whole process again, but just as before, I have 2 cases. Now this is an even number of ones, and this is going to be an odd number of ones. So now the transition here, the transition is going to go from Q2 to Q3, and you're going to use the ones to change the parity. And the zeros are going to make you stay at the same spot because they don't change the parity of the number of ones. Okay. So now if we try to combine those 2 ideas together, I don't want to show you the answer, but I want to create a DFA. Now this kind of looks weird. I want to create a DFA, M, such that the language accepted by M contains an odd number of zeros and an even number of ones. So how much time? So how could we make a DFA that could accept a language like this? Well, just like, so I'm not going to show you the answer. I'm going to do it kind of with you. So remember, what I'm looking for is I'm looking for an odd number of ones. So an odd number of, zeros. Yeah, zeros. And even number of ones. Okay. Okay. So Before, what was happening is I had two cases, right? I had even number of zeros, odd number of zeros, or the same thing for ones. Now what's actually happened is I have four cases. So if I write a number of zeros here, this is a bit big, and number of ones here, then I can have an even number of zeros and ones. And then I can have an even number of zero, odd number of ones, odd number of zero, even number of ones, and odd number of zeros, odd number of ones. Okay. And what I'm looking for, the case that I'm looking for is this guy. So I want, right? I just want to make sure odd number of zeros, even, yeah. So I want an odd number of zeros and an even number of ones. Okay. So I have four cases. So this is an indication. This is a very good indication that I probably need four states. Okay. So my first state Q0, is going to correspond to which case? Well, remember when you're in Q0 at the very beginning, if this is your input, your cursor starts before it, right? So your cursor is getting ready to read some strings. And at this point, you have a string of length 0. So you have no zeros and no ones. So you have an even number of zeros and an even number of ones because 0 is even. Okay, so Q0 is actually going to correspond to the case where you have an even number of zeros and an even number of ones. Okay, so now that you're at that state, I want to create the transitions to go from that state to all the other states for the cases, right? So now suppose I have an even number of 0 and an even number of ones, and I want to go to Q1, which I'm going to make the case for an odd number. So this is going to be an odd number of zeros and an even number of ones. So how can I go from Q0 to Q1? Well, what you need to yes, so just before I start, Kimberly's question, the number of cases was kind of a direct indicator of how many states I would need. Because in this type of example, every state is a case. That's what's going to happen here. So here, so now coming back to the DFA, I'm in Q0 and I want to go to Q1. So what I want to do is I want to flip the parity of my zeros from even to odd, but I want to keep the same parity for my ones, so from even to even. So in other words, to go from Q0 to Q1, I'm fixing the number of ones. So the number of ones is fixed, and the only thing I'm changing is the number of zeros. So if I'm even in Q0, then if I read a 0 and go to Q1, I'm definitely going to be odd because I'm adding 1 to an even number, so that's an odd. And now if I'm odd and I read another 0, I'm adding an extra 1 to my number of zeros, so that's going to give me an even number of zeros, right? So that's why I go back to the case even. Okay, and essentially now I just apply there should be 0 here. I apply the same logic to go to all the other cases. So let's say that Q2 is going to be the case where I'm going to keep the number of zeros constant, so it's going to stay even, but the number of ones is going to switch to being odd, okay? So that means to go from Q0 to Q2, I'm going to keep the number of zeros fixed, and the only thing that's going to change is the number of ones. I'm going to add an extra 1, so I'm going to go from an even number of ones to an odd number of ones. And then from Q2 back to Q0, I'm again going to read a 1 to go from odd to even. Okay, and so I keep this process going. Suppose I'm in Q2, so I have an even number of zeros, odd number of ones. Then I go to Q3. So Q3 is the last case. It's an odd number of zeros, odd number of ones. Okay, so what do I keep fixed here? I keep the number of ones fixed. It's going to stay odd, but now I'm going to flip the parity of the zeros from even to odd. So you can kind of see how this axis here is for the parity of zeros, And this axis here is for the parity of ones. Okay. And so again, to go from, let's say, Q3 to Q1, that's the last case. I need to go from Q3 to Q1. So keeping the number of zeros constant, so odd, I need to flip the parity from odd to even by adding one, and from even to odd by adding a one. Okay. And so this is how you would construct your four states. Now, a question for you: if this is my DFA M, is L of M equal to L? So I actually want someone to answer this because it's a good question. Let's see why. Okay, excellent. Someone. Okay, I wanted someone to say yes, but the reason why this is false, the reason why this is actually not true, is because I have forgotten something. Yes, very good. I have forgotten something. I have forgotten to put a final state. So I have no final states. If I have no final states, L of M is actually just going to be what? I'm not going to accept any strings, right? I'm not going to accept any strings. So the language accepted by M is going to be the language that contains no strings. And that language is called the empty set. So it's the empty set for the language. So right now, as it stands, the language accepted by M is the empty set. But I can change that very quickly because remember, I want an odd number of zeros and an even number of ones. So to change that quickly, I'm just going to add a final state to the case that I want. And to the case that I want. And that's going to now, so now this is going to be true. So this is going to be true, and this is obviously going to be false. And David, is the empty set and the lambda the same thing? That's an excellent, excellent question. So, so is the empty set and the set containing lambda the same thing? So the answer is most definitely no. The empty set is a set that contains no strings, and the set that contains lambda is a set that contains one element. So clearly, even if you look at the cardinality of this is 0, the cardinality of this is 1. And do I have time to give you this? Not really, but if I wanted to construct a DFA that accepted the empty string, I could actually just write, let's say my alphabet was 0, 1. Then I could just write, if this is my initial state, I could just say this guy here, this machine, this is a valid machine, right? I have an initial state. I have 2 transitions for each state because I only have 1 state, but I have no final states. And actually, this machine here, the language accepted by this machine, I'm sure Dr. Shearer must have talked about this in the lecture, but just to reemphasize it, the language accepted by M here is the empty set. Okay, because no matter what you read here, right, you're going to read anything, you're always going to end up in Q0. And once you end up in Q0, you're going to not be a final state, so that's going to be a reject. However, if you wanted to create a machine M, where L of M was equal to the empty set, how would you do that? Well, the only way in a DFA that you can accept the empty string is you make Q0 a final state, right? You make Q0 a final state, so you read a lambda. That means you don't move, basically. You don't move because the empty string has no symbols, so you don't move, so you stay at Q0. And then anything else, so anything else after the lambda is going to be rejected, okay? So this would be the DFA M, a DFA, so there exists more than one, but this is a DFA M such that the language accepted by M is the what? The empty string, yes. And so clearly we can already see that these two things are not the same just because this has one final state and this has none. Okay, that was a massive tangent. Sorry about that. It just got me really excited. But now an exercise for you. Maybe take, okay, so now that we've essentially talked about a couple of ways of constructing DFAs, I'll give you maybe, if you have maybe a sheet of paper and a pen, I'll give you 2 minutes 2 minutes, maybe a minute, to try to create a DFA that accepts the language L here, and just note here that the alphabet is AB, so your transitions should have A and B. Okay, so 1 minute. Okay, so it's been maybe a few seconds just to think about it. Okay, so oh wow, you're okay. Well, that's the first time I've ever seen someone write a DFA in a chat. I like your determination. Okay, maybe. So it's a good idea. So let's look at the solution together. So what is my language here? What are the strings in my language? Well, they are any strings that look like they start with A, and then they have the sequence of ABs. So ABs, right? Where there's n ABs for n greater or equal to 0. So notice this could be lambda. This could be the empty string. And then after that, you have an A and an A. Okay. So that's essentially what the DFA, what language strings the DFA should accept. Okay. So another trick here that I'm going to talk about is looking at the shortest string in your language and seeing what is the shortest string that should be accepted by your DFA. In this case, the shortest string is AAA. And I'm actually going to use AAA as a building block to create all of my other structure. Okay, so because if my DFA doesn't accept A cube, then for sure it's not going to be the correct DFA. So I'm going to start with the DFA that accepts AAA. So I'm going to start by creating the transition functions, the transitions required for that. So I start at Q0, then I read an A, so I go to Q1, I read another A, I go to Q2, and then I read another A, I go to Q3, and Q3, at that point, I have 3 A's, so this should be accepted, right? So that's a building block, okay? Now, where do I go from here? Well, I can start back at my initial state, and notice that, again, there are 2 cases because now I have a binary alphabet, so I have 2 cases to consider. Either my string W is going to start with an A, or it's going to start with a B. So what happens if it starts with a B? Well, it doesn't look like anything, B and then something doesn't look like anything in the language L. So that's definitely going to be, no matter what comes after the B, it's going to be a reject. So if I'm in Q0 and I see a B, I can go to another state here, and that's going to be a trap state. It's going to be a dead configuration because as soon as I'm in Q4, and as soon as I've read a B, I can't get out of that situation. I'm going to reject no matter what, okay? So that essentially clears the case for Q0, right? So now suppose instead of having an A first, I actually have a B. So I'm in Q1, but now instead of AA, I have AB, right? So what happens if I have AB and then a bunch of other things? Well, AB, if my string starts with AB, that doesn't actually correspond to anything. Again, that doesn't look like anything that's in here. okay? Because remember, my string should look like A and then AB. So there's kind of like an A missing here. And because of that, I'm going to reject anything that looks like it starts with AB. So that's why that if I'm in Q1 and I read a B, I'm going to go to a trap state. Okay. So for Q1 now I have 2 transitions, so that one's valid, right? So now suppose that instead of having AB, I have A and then A. So that means that I transition to Q2, right? Now I'm in Q2. If I see an A, I go directly to Q3 because possibly that's the end of my string and then I would accept it. Otherwise, if there isn't an A in the 3rd position and rather there's a B, then what I need to do if I'm in Q2 is this AB might be the beginning of a sequence of a bunch of ABs. And so to check if it's a sequence of a bunch of ABs, then once I see Q2 and I see a B, I'm going to go back to Q1. So hopefully you can see that this is going to look like, so I'm going to, once I'm in Q1, I know that I've read an A, then I'm going to read an A and a B. So I'm going to read an A and a B. So I'm back in Q1, then an A and a B. So I'm back in Q1, then an A, and so you kind of get it. You continue until you hit your last AB. So once you hit your last AB, you're back in Q1. Let's say again you read an A. So again you read an A, so now you're in Q2. Then you read another A, so now you're in Q3. So right now, this is a string that should be accepted. So it looks like we're good. This should be a final state, right? But now the thing that's going to make it a reject is if, for instance, I have an A or a B here, well, my string is no longer going to look like a bunch of ABs, and then AA. It's going to look like a bunch of ABs, AA, and then either A or B. So that definitely is not going to be an L. So if that happens, if I'm in Q3 and I see an A or a B, I'm going to also reject. Okay. And for each state here, I know that I have exactly 2 transitions. So this is a valid DFA. And in fact, L of M is equal to L. Okay. So Alec, I'm not sure. Yeah, it seems like you're missing a state because I'm pretty sure you definitely need at least 5 states for this because of the trap state. Should Q0 be an accept state because we accept lambda? Well, we do not accept lambda. So remember, the shortest string accepted by this DFA should be AAA because the shortest string in this language here is AAA. That's when n equals 0. Okay, there isn't anything shorter than AAA. But so maybe what's confusing you is that when n is 0, this is lambda, right? So what you have is A lambda AA, but that's the same as AAA. Okay, so hopefully that clears it up. Okay, great. Okay, so how much time do I? Okay, so obviously I think it's clear that I'm going to go over the time. I'm going to try to finish. Yeah, it's only 2 exercises, so I think I'm going to. So hopefully, if you guys can stay with me, I'm just going to go over regular languages. Each state, yes, that's a good question. For DFAs, not for NFAs. NFAs, it's a different kind of issue. For DFAs, if your alphabet is AB, then the number of transitions, well, actually, the number of transitions from any state should equal the cardinality of your alphabet. So in this case, because you have A and B, you have 2, and you should have 1 transition from A and 1 transition from B. So yes, this is for DFAs. For NFAs, you don't need that, and you're going to see in kind of the recorded material that I talk about that it's different from a DFA. Okay, but again, we can talk about the NFAs. If you have any extra questions, we can talk about it in tutorial 3. Okay, so I hope that clears it up. Okay, So the next thing and the last thing that I want to talk about in this tutorial is the concept of regular languages. So what is a regular language? Well, there are actually many ways to prove that a language is regular, but the initial definition that you're also given in your lecture of a regular language is a language L such that there exists a DFA M where L of M is equal to L. So meaning that if you're given a language L, okay, and the question is prove L is regular, okay, then one way of doing this, so there are actually many ways that you're going to see, but one way of proving this is you create a DFA M such that L of M is equal to L. And this would prove that the language L is regular. Okay, so now let's look at some, two examples. Well, an example and then an exercise for you, if we have time. So we're given the language L here over the strings 0, 1. And the language is all of the strings over the alphabet 0, 1, where that string contains 0, 1 as a substring. Okay, and the goal is to show that L complement is regular. Okay, so that's the goal. So remember, just FYI, well, not FYI, just recall that L complement is sigma star minus L. Okay, so how do we do this? How do we show that L complement is regular? Well, so the first way is we build DFA M such that L of M is equal to L complement. Okay, so what is L complement? L complement is going to be the strings over 0, 1 star such that 0, 1 is not a substring of W. So you can build a DFA M that accepts this language. Okay, so that would be one way, which I'm actually not going to do. I'll leave that as an exercise for you. What I'm going to do is I'm going to give you a trick for DFAs where you want to show that L complement is regular. So the other way is you build, whoops. Okay, my pen is, oh god. Okay, I have no idea what just happened there. Okay, everything is fine. Everything is going to be okay. So you build a DFA M such that L of M is equal to L. Okay, and then you take that DFA M and you transform it by taking the non-final states and making them final states, and you take the final states and make them non-final states. Okay, so this would be another way of building a DFA M such that, so now this is going to be, you're going to transform your DFA M, and let's call that transformation M prime. So then L M prime is actually going to be L complement. Okay, so let's do that. So first, so this would be step 1 and this would be step 2. So the first step is to build a DFA M that accepts L. Okay, so here I want to accept all of the strings that contain 0, 1 as a substring. I'm going to do this a bit faster. So I start in Q0. If I see 0 and then 1, then I accept, and I accept anything that has a 0, 1. So that's going to be, well, I'm going to put a self loop there. And then I fill in the gaps, right? So if I'm in Q0 and I read a 1, well, I'm just going to stay in Q0 because the 1 doesn't help me in my search for 0, 1. Okay. Now suppose I've read a bunch of 1s and now I saw 0, so now I'm in Q1. Now, if I see a, if I see a 1, I definitely go to the accept or the final state. If instead I see a 0, if I see a 0, well, I don't actually have to go back and reset. What I can do is I can stay in Q1 here. I can stay Q1 because I can keep reading a bunch of zeros, and as soon as I see a 1, I can go directly to Q2. Okay? So then this guy, this is the DFA M, such that L of M is equal to L. Okay? And now what I need to do is I need to do my transformation. So because I'm lazy, I'm going to do it in place. Q2 is a final state, so I'm going to make it not a final state. Q1 is not a final state, so it's going to become a final state. And Q0 is not a final state, so it's going to become a final state. Okay, and so this machine M prime, the language accepted by M prime is going to be L complement. Okay, there's a proof for this, but I'm going to skip it just for your sake, and mine as well, actually. But essentially, now that I've created this machine M prime, I have a DFA such that the language accepted by M prime is L complement, and so this implies that L complement is regular. So I have proved this. Okay, so this might seem a bit weird because really it's just we're doing the same thing as before. But you're going to see that there are different techniques to showing that something is regular, and this is just the first one. So we're just trying to show you the first way of showing that something is regular, and then you see you can build on that one. Okay. Okay. So, and also one other very important thing is you can do this for a DFA, but you cannot. So this is only for DFAs. Okay, you can't do this switching the final to non-final for NFAs. Okay, so beware. This is a very common kind of mistake that students make. Is they see an NFA and they do this process and they say, okay, now I have L complement. No, in fact, you can only do that if it's a DFA. All right, so just I want to make that 100% clear. All right, okay. So I hope that's clear. The last exercise that I'm going to do is this one, yeah, because I'm out of time. So I want to show that the language L, which is a to the n, where n is a multiple of 2, but not re, is regular. Okay, again, so again, what's a way of doing this? One way to show that L is regular is to find a DFA M such that L of M is equal to L. Okay, so how are we going to do this? Well, in this case here, for these kinds of DFAs where you're dealing with kind of n and you want multiples and things like that, it's a lot easier to start with writing out some of the numbers and seeing if there's kind of like a modulo kind of pattern. Okay, so let's say I have n here. I'm going to write a few values of n. So let's say the first 6. So now, if I have a to the 0, so that's lambda. 0 is a multiple of 2, and it's also a multiple of 3. So it doesn't respect this part of the definition. So this would be a reject. 1 is neither a multiple of 2 or 3, so this would be a reject. 2 is a multiple of 3 and not a multiple of 3. Is a multiple of 2 but not of 3, so this would be an accept. 3 is not a multiple of 2, so that would be a reject. 4 is a multiple of 2 and not of 3, this would be an accept. And 5 is prime, so it's neither a multiple of 2 or 3, this would be a reject. So now that you've done the first 6, what you're going to notice, and you would notice this by kind of writing a few more out, is if you write out 6, 7, 8, 9, 10, 11, you're going to see that the pattern repeats. So 6 is a multiple of 2 and 3, so it's going to be a reject. 7 is neither a multiple of 2 nor 3. It's going to be reject. 8 is a multiple of 2 and not 3, except. This is going to be reject. 10 is divisible by 2, but not 3, so it's going to be accept. And 11 is prime. So now we see that we're repeating this, and we're actually repeating it mod 6, okay, modulo 6, right? So all I need to do here is I just need to create a DFA that where for each state represents n mod 6 equal to something, okay? So I'm going to need how many states? Well, probably 6. I can't think of it off the top of my head, so let's just do it. So this is going to be equivalent to n is equal to 0 mod 6. Then you read an A. This is 1 mod 6. Then you read an A. This is 2 mod. Sorry, not 2 mod 6. This would be, yeah, okay, sorry. This is 0 is equal to n mod 6, and this would be 1 is equal to n mod 6. Yeah, sorry about that. 1 is equal to n mod 6. This is 2 is equal to n mod 6. Okay, and then you keep going. So this is an except, right? Because it's this case here. So you read another A, then you read another A. So this is for 3. You read another A. This is for 4. You read another A. This is for 5. And then you complete the loop going back to your initial state. And so this is a DFA M. So M is a DFA such that L of M is equal to L. So this implies that L is regular. Okay, and that would complete the proof for showing that L is regular. Okay, so as I said, I obviously don't have time for NFAs and NFA to DFA. There's a pre-recorded video that I have that I'm going to post for you. And if it seems like it's necessary, we're going to talk about NFAs and NFAs to DFAs in tutorial 3. Okay, but yeah, so there aren't any other questions. So are there any questions about the assignment or the quizzes or any material that you would want me to answer? Okay, so it doesn't look like it. So all right, well, just look at, did anyone private message me? No? Okay, all right. So so yeah, so that's it for me for this tutorial. I hope you have a nice week, guys. Good luck in your quiz, and I'll see you in tutorial 3 on Monday. All right, take care, everybody.